Topic 12.3 Rectilinear Kinematics Erratic Motion. Objective is determine the position, velocity and acceleration of a particle using graphs. So until now we have dealt with problems where either position, velocity or acceleration was expressed as a function of time. So either S, V or A were given as a function of time using a fixed equation, and then we calculated the other two parameters by taking derivative of or integration of mathematical equation. But oftentimes in many practical situations, this information, position, velocity and acceleration relative to time is generated in the form of a graph, and it's more intuitive and easy to generate graphs than deriving mathematical equation. For example, this train is traveling on a straight track, and it's easy to measure the position of the train relative to time and plot it graphically. So when the information is being presented as a graph, how do we calculate the other two parameters if one of the parameters is known? That's what we will study in this chapter. And there are 5 different types of graphs that we will study. So position as a function of time, velocity as a function of time, or acceleration as a function of time. And then there are 2 spatial graphs where position is given as a function of velocity is given as a function of position and acceleration is given as a function of position. So I have a couple of YouTube links in this slide. So if you just Google search for any like space rocket launches, you will see that during the launch, the velocity, altitude, acceleration, and time of the rocket are being reported. And once we have those data, we can, using the different types of sensors, those data are being recorded and they can easily be plotted as a graph. And for that information, we can plot the data graphically and derive the other parameters for the kinematics quantity. So look at this example here that a truck is traveling on a rectilinear motion, and the velocity versus position of the truck is given. So this is easy to generate because if we have a GPS records both the speed as well as the position. So using GPS, we can acquire this data and plot it graphically. And we can see here that the speed of the truck increases relative to position for first few feet here, 625. But then the speed remains constant, so truck travels at constant speed for the remaining of the distance up to 1500 feet. So now this is position versus velocity versus position graph. How can we generate acceleration versus position plot from this given graph? That's one question. Look at the another example that velocity of the car is represented as a function of time graphically. And we can see here that y-axis has velocity, x-axis has time. And this line shows that the velocity increases for first 5 seconds. And then the car travels at constant speed, and then its speed decreases and becomes 0. This is very common for most of the vehicles where starting from race their speed goes up, then the vehicle goes at a constant speed, and then speed drops and it becomes 0. So how do we calculate position plot, like position versus time graph or acceleration versus time graph from the given velocity graph? This is similar example that we discussed at the beginning, like the train position versus time. So to generate, what we need to do is, if we have position versus time graph, to generate velocity graph, we need to take the derivative. But what is the derivative of a graph? So derivative of a graph is nothing but the slope of the graph at that point. Basically, it's the line tangent to the motion curve at that point is called the derivative of the graph. So if we have this blue graph here, and we need to generate the velocity versus time graph, we need to divide the position into series of time segments like t1, t2, t3. And at each time segment, we draw a tangent or find out the slope of the graph. And that slope, whatever is the magnitude of that slope, we mark one point in the velocity graph. We do that same for the other point. We do that same for the third point, and then we join this series of like slope points and generate the velocity graph. So derivative of a graph is nothing but the slope of the graph at that point. Okay. Now, once we have velocity graph to get acceleration, we do exactly the same thing. We find out, we divide this into series of like timestamps, and at each time we calculate the slope of the graph and plot those slope on the acceleration plot and join those points to get the nice smooth curve for acceleration. Now, this is much more easy to do using like software such as MATLAB or Python. But we can also do this manually by calculating the points and joining those points with a smooth curve. How do we do the reverse? If we know acceleration as a function of time, how do we get the velocity? Now, if we have an equation for acceleration, to go from acceleration to velocity, we do integration. But what is integration of a graph? So integration of a graph is nothing but the area under the graph. So here also we do the same thing. We divide this acceleration plot into series of timestamps t1, t2, like t3 and so on. And for each timestamp, we calculate the area under the graph. And that area we add to the initial velocity. So if we know the previous velocity is v0, whatever is this area, red portion, we add that red portion to v0 and we find out a new point at that time, t1. Now to get the velocity at t2, what we need to do is we find out the area under the graph from t1 to t2 and add that number to the last velocity or previous velocity, which is v1, and generate another point for t2. And we do repeat that process for all the remaining points and then join those points using a smooth curve to get the velocity graph. So integration of a graph, so this is the sign of integral of a graph, is the area under the graph. Okay, so we apply that concept to, let's say we know acceleration as a function of, now let's talk about the two spatial graphs. So if we know acceleration as a function of position, how do we calculate velocity as a function of position? So for that, this is the equation that we need to take as a reference, that is ADS equal to VDV and integral sign on both sides. So ADS is this plot. So area under ADS gives us integral VDV. Now, if we substitute limits here, V0 and V1, and integration of V is V square by 2, and after substituting the limits, we get 1/2 V1 square minus V0 square is equal to area under the graph. So if we know the initial velocity V0, let's say V0 is this point, then the next velocity V1 at position S1 we can find out by integrating this graph. Whatever is that area under the graph, we apply this equation to that area and calculate V1. So that's the velocity at point S1. Now we do the same for the remaining points. So to get the velocity at position S2, once again we find out the area under the graph between S1 and S2 and apply this equation, 1/2 V2 square minus V1 square, where V1 square is now known velocity and we calculate V2. So we at each point we calculate velocity using this equation applied to area under the graph and adding and substituting the value of the previous velocity. So we do that and we get series of points, and then for all those points we join and get the nice smooth plot. And for the final graph, velocity versus position graph, and getting an acceleration versus position graph from that, we need to again rearrange that previous equation in the form of v multiplied by dv by ds. So if we have this information, velocity as a function of position, and we would like to calculate acceleration at a specific position, what we need to do is we first calculate velocity at that position from the graph. So you just project the given position onto graph and read the value of velocity, and you multiply that velocity with the slope at that point, and whatever is the answer is the acceleration at that point. Okay, so to get the, let's say, acceleration at another point, again, we find out the velocity at this point and multiply by that with the slope of that point, and we get another plot on the acceleration graph. And we join those series of points to get the acceleration graph.